talk about hybrid music recommenders. And hybrid music recommender is an impelling need nowadays with the overwhelming amount of multimedia data. Users really need a guide, a tool to discern and to find what they really want in this huge amount of data. And many platforms have been developed through the years, like as you can see there are a few examples here like Spotify or Last.fm, websites that provide this service to users. But it is also a compelling task, really challenging one, because modeling users' preferences and tastes in fact of music is not easy, because it's in such a personal and subjective thing like music and art is not easy. And before moving on, let's take a look at the basic methods, some preliminary knowledge. These are three methods: collaborative filtering, content-based, and social approach. And with this we will build hybrid combinations, because they showed that better performances combining these basic methods, because we will see that they have some drawbacks, each of them for different reasons. And with this hybrid combination we will try to overcome these problems. Let's take a look at collaborative filtering. This is the first we'll see. Collaborative filtering, the main idea behind it is to give ratings to items, relying on other ratings of other similar users. And you can divide this collaborative filtering approach in memory-based and model-based. Model-based is practically based on a machine learning, so you have a model to train, and while memory-based is based on history of users. The drawbacks are called starch, popularity bias, human effort, if you have to explicitly rate items, or sparsity of the user item matrix, or model complexity if we're talking about model-based systems. Let's take a look at this user item matrix. As you can see, there are a lot of zeros. It's just a toy example, but you can see that the sparsity of the matrix, because you have lots of items, millions of songs in a database, and just I don't know, a few thousand users. It depends on how successful is your system or your platform. So you predict unknown ratings based on other users' ratings. The other method is content-based. Content-based methods relies on signal processing techniques. We have a few here, like melt frequency, Chebyshev coefficients, or short-term Fourier transform features, or wavelength coefficient histograms. The drawbacks is kind of a low serendipity, has been pointed out, because you can it relies it has a small scope, so you can just see and extract features, acoustic features like timbre features or pitch features from the signal. You don't have high-level features you can extract from it. So these are the main drawbacks. And social approach is quite recent approach. It tries to model friendship relations between users, and from that, or our collaborative actions like collaborative tagging. And we can divide it in text-based and co-occurrence-based. Text-based is it comprises collaborative tagging techniques or mining of microblogs. And the co-occurrence-based are instead peer-to-peer shared folders or playlists or web data. The drawbacks is complex modeling of relations, because it's not always true that if your friend like a different, like a kind of music, a genre of music, not really straightforward that you will like the same, and it's just one of the problems. And integration with other methods like collaborative filtering and content-based is also a problem, because you have a huge amount of data here, and many kind of relations, tags, users, tags and tracks, whatever, and you have to weight them and combine them together, and it's not easy. And time complexity too, because if you want to have an online, on real-time application, these methods usually relies on graph. They are graph-based, and time complexity could be an issue. Here we can see some the intersections. We have the hybrid solutions. I will spend a few words on that. The first one is content-based plus collaborative filtering. We have 5 solutions that I analyzed. Is music recommendation system based on music and user grouping. Is quite an early work. It's dated to 2005, and it works with MIDI files, so it's kind of yeah, it's really early work. But it gives the picture, because it uses 6 features extracted from the MIDI files, and it groups these features in K music groups, and it uses 6 thresholds to do that, and it also computes centroids to do this kind of clustering. And the ranking is done instead with switching, so they are not combined in any way, between content-based collaborative filtering and statistic. It tries to tackle the problem of time-dependent collaborative filtering, but it's just a coarse way to do that, because other techniques have been developed. Hybrid social acoustic recommendation system for popular music. Instead, it tries to resolve the problem of long tail recommendation. So it tries to model the user needs using a unique feature vector, exploiting popularity. It's called social in this case. Probably I would call it popularity, because it builds concurrent matrix, adjacency matrix A. It factorizes it with an eigenvalue decomposition, and it extracts also acoustic features from the playlist that the user submits to the system, and it compares them in order to give with a weight for dynamic adjustment, a weight to popularity features or to acoustic features, in order if the user maybe he wants to listen to popular music. So for the weight and the ranking, it gives different weights to these different features. Another work is hybrid retrieval approaches to geospatial music recommendation. The main idea behind this work is to integrate geospatial information with collaborative filtering method. It uses a geodesic distance, and the geospatial weight is given to the collaborative filtering ranking through in a Gaussian fashion or a linear fashion. And it's not really stated which is the best one, because it really depends on the density of the agglomeration in which the user lives. So it's not really stated. But it's one of the first works that exploits this kind of information, this kind of interaction associated information, because there are many sources of information, side information like item side or user side, that try to depict the context of items or users, and there are also interaction associated information that tries to depict the context at the moment of the fruition of the music of the product. This is another work. The main idea behind it is that it assigns different weights to the different acoustic features, because the idea is that different users have different sensibility to acoustic features. So maybe if a user has a certain preference is because he has like his ear is trained to listen to certain features instead of others, or he weights them more. So for the slate code recommendations, it's better to give different weights for the different features. And Laplacian graph is used to do the ranking at the end with a Green's function for linear influence propagation of the rankings, of the ratings. And then a shortest path algorithm is used to find the M closest song to the seed song. Yeah. Another work is hybrid collaborative and content-based music recommendation using probabilistic model with latent user preferences. It's a long title, and this is a collaborative filtering technique, model-based one, and it exploits also content-based features because it uses a three-way aspect model. This model was firstly devised for documents, so for text. So it tweaks a little bit it with watching at songs as a bag of timbers. So polyphonic timbers receive a weight, and this is done through Gaussian mixture modeling to assess the distribution of this polyphonic timbre throughout the song. And the idea is that that these latent variables represent the user's music preferences. So the association between music preferences and acoustic features, or the association with the output of the system, is not really explained because it's just a probabilistic model. So it's not so clear why a user would prefer a certain timbre instead of another. To do so, yeah, latent variables are kind of genre. They represent the genres that the user may like. To do so, expectation maximization techniques is used to tune the parameters of the Gaussian mixture models, because they have to be the same in order to do comparisons. So it's fixed Gaussian mixture model, and the log likelihood function is maximized, and it depends on users' rating, so collaborative filtering, and polyphonic timbre weight. Let's move on with collaborative filtering and social approach. We have three works. The first one is on social networks and collaborative recommendation. It uses random walk with result technique to measure relatedness on graph, because it exploits a graph, a simple graph, that it can be represented by a matrix S that comprises the sub-matrix user track, user tag, track tag, and it tries to measure the relatedness between these items, these objects. A normalization of matrix S that comprises these other submetrics is needed because of the range of the values that this association these relations have, like in a user-user, we just put a one in to depict the friendship relation between them, but user track is just, as we saw before, is the user item matrix basically, and it has the frequency of the play count of a user to a certain item, so it could have values bigger than one. So sort of normalization is needed, and also the restart parameter is has to be tuned in order to give more personalized or information or recommendation to a user. The other method is ternary semantic analysis of social tags for personalized music recommendation. It is an important work because it tries to expand the user item matrix, giving a third dimension to it, and it builds a tensor. It is a user item tag matrix, and then it tries to draw information from it with a higher order SPD, which is a generalization of the well-known SPD decomposition. It is done in order to cope with the problem of sparsity, problem of we saw it of the collaborative filtering method, and it also uses a tensor reduction algorithm, which is a kind of a low-rank approximation that we used to do with SVD. So the association are estimated with this tensor reduction algorithm, and the ranking is based on the weights that of the pair user tags. So the recommendation here is done through tags, and not it's not it doesn't consider content-based information, but only tags, because we're looking at collaborative filtering and social approaches, a hybrid approach. And it's not so, it's kind of a strong assumption here, because we just discard content-based information, and we say here tags can replace content information. Is that true? We will see. Another work is Contextaware music recommendation based on latent topic sequential patterns, and it's once again it is a model-based collaborative filtering, because it assigns tags to songs with a latent Dirichlet allocation, and each topic has K tags to represent it, and songs features are represented by tags as well. And a sequential pattern mining technique is used to compare the active session of a user with the playlist, the patterns stored in the database, in order to give the recommendation. So if there is a match between this pattern, you give a weight, a context score to it, and then it linearly combines it with a CF ranking that is done with a KNN method. It's just a typical CF ranking, and then it post-filters it. And it is important because it tries to model context changes with a probabilistic approach. Here we have content-based, collaborative filtering, and social. We can see an important work, really important, music recommendation by unified hypergraph, combining social media information and music content. This is important because it takes a step ahead of the simple graph, and it builds an hypergraph to represent high-order relations. So now vertices of the graph could be any object, and the hyperedges are non-empty subset of vertices. So this is done to in order to assess the different relations between different objects. In this work, there are 9 kinds of relations, because the objects are tags, users, tracks, and groups. It is an important thing because it also this method could give multi-output recommendations, not only tracks but also tags and groups, because with HyperEdge you model each relation. There is a cost function for ranking. I'll not go into mathematical details, but anyway, and also weights and of hyperedges and normalization, because you, as before in the graph-based random walk with the start method, it had a graph with submatrices, and the relations between different kind of objects have to be weighted. In this work, they do a normalization with the cardinality of the hyperedge, so it kind of treats all the relations in the same way, equally. This other work, Location-aware music recommendation using auto-tagging and hybrid matching. The important idea is that it counts for POIs, it stands for points of interest. So it tries to give recommendation for a specific point of interest, where it could be the Eiffel Tower, like before. It tries to do that with a collaborative tagging to associate tags with POIs, and also a knowledge-based technique is used to find the matches between artists and POIs. But an important thing, I think, is the auto-tagger. It is important because it relies on CP method, content-based methods. So it is trained, and it is trained to give tags to songs analyzing the signal. And it is important for scalability, because in this work they have just 3 tracks per artist, and the artists are in the order of 100 or something, and the points of interest are, I think, 35. So it's really small data set, but the auto-tagger could be a solution for scalability. Let's move to discussion and future work. Here we have all the papers I went through in these minutes. The problem and the future work is toward going to step over the user item metrics as it was typically devised. So including information, exploiting other information, side information, or interaction associated information, in order to get the best from the different relations between objects. And it is also important because user item is really sparse, so it affects the output of the recommendation. Long tail issue is another important thing, because giving a recommendation to a user is not easy, and if a user wants to hear popular music, or he wants to enhance serendipity in his experience, is important, and the model should keep up with changes, and with also providing long tail recommendations or items. Parameters tuning, scalability, and time complexity is also an important thing, and we know that probabilistic models they have many parameters to be tuned, and so often they're used offline for the training. But in this work, this is the hybrid collaborative and content-based music, there are other two works linked with it from the same author of it, and they try to find an incrementally trainable model for that, considering the option that a user can give ratings to different items online. So you have to update your model and recalculate all the parameters. And they devised a solution which is O of delta M, where M is the number of different ratings, new ratings that could run on in real time. But they didn't consider the new item problem, so it's still a work that has to be done to retrain the model with different users or different items. Time complexity is also an issue with big systems. Graph-based, as I said, graph-based are really complex usually, and they require a lot of time to be trained and to be used. And also tag-based and content-based. There is a difference, a semantic difference, because content-based can extract low-level features from signal, while tag-based are more on a high level, like mood or something else, and they are really noisy if there is not a controlled vocabulary. So a lot of work still to be done, also to assess if tag-based can replace content-based. I think the best solution is just to try to exploit all the information with algebraic solution, with tensor factorization, matrix factorizations, or probabilistic matrix factorization, in order to get the best from these models, from these matrices. That's pretty much the picture of the topic I wanted to present.